Multivariable Calculus, Section 14.4, Green's Theorem. And from Wikipedia, George Green, 1793 to 1841, was a British mathematical physicist who wrote an essay on the application of mathematical analysis to the theories of electricity and magnetism. The essay introduced several important concepts, among them a theorem similar to the modern Green's theorem, the idea of potential functions as currently used in physics, and the concept of what are now called Green's functions. Green was the first person to create a mathematical theory of electricity and magnetism, and his theory formed the foundation for the work of other scientists such as James Clerk Maxwell, William Thomson, and others. His work on potential theory ran parallel to that of Carl Friedrich Gauss. Green's life story is remarkable in that he was almost entirely self-taught. He received only about 1 year of formal schooling as a child, between the ages of 8 and 9. Some notation. Given a region in the xy plane, bounded by a simple closed curve C, which can be smooth or piecewise smooth, then the integral f dot TDS, which equals integral P dx plus Q dy, is the line integral that computes the work done by f, which equals Pi plus Qj, in moving a particle along the curve C in the counterclockwise direction. That's what the little circle means on the line integral. If you see a little circle on the line integral, that means that you are moving along the curve in the counterclockwise direction. So for example, here's a region in the xy plane called D, and it's bounded by a piecewise smooth curve made up of C1, C2, C3, and C4, and those little arrows are pointing in the counterclockwise direction, showing the parametric orientation of that piecewise smooth curve. The boundary curve is said to be positively oriented if it has a parametrization that is counterclockwise. So counterclockwise curve and positively oriented boundary curve mean the same thing. Green's theorem. If C is a positively oriented smooth or piecewise smooth simple closed curve that is the boundary of a region R in the xy plane, and functions p and q have continuous first-order partial derivatives on R, then we have his big theorem, which says you can take the line integral of p dx plus q dy and instead compute the double integral on the region bounded by C using the partial derivative of q with respect to x, which is kind of backwards, that's not intuitively obvious, minus the partial derivative of p with respect to y, and then integrate that with respect to the area of region R that's bounded by the curve C. So now, for example, let's say we have a nice smooth curve, and this particular region would be very difficult to set up to figure out area because it's not vertically or horizontally simple. But if you have a parameterization for C, you could easily change that first line integral into parametric form and integrate. So you wouldn't want to use Green's theorem. However, if we have something like this, a region like this, which has several different curves, you'd have to do 4 separate integrals using a line integral. But using Green's theorem, you can do it all in one fell swoop. And so depending on the region you're looking at, one of these two integrals will be easier than the other. And of course, in this section, we're going to be using the second one a lot. Now here are 2 more regions. Which one would you want to use a line integral on, and which one would you want to use Green's theorem and integrate over the area instead? Well, the first one you'd want to use a double integral and integrate with respect to area, because otherwise you're going to have to do 4 separate integrals. The second one, however, has just a single nice positively oriented smooth curve, and it would be easier to use the curve than to figure out a formula for the region. Okay, now here's a region that has an inner boundary and an outer boundary, and you'll notice that the outer boundary goes counterclockwise, but the inner boundary goes clockwise. So you might think, well, can't do it then. Well, this is sometimes you can be very clever. For example, if you split it into two regions and introduce C5 and C6 forwards and backwards, now the top half, you can do the entire top half region going counterclockwise around the top half, and you can do the bottom region going counterclockwise around the bottom region. And so you could split this into two problems and use Green's theorem and integrate over the area. This donut divides into two simple positively oriented regions, and therefore you could apply Green's theorem. You just have to do two separate problems. One more little comment on this donut region. If you were to use two line integrals, notice that you would still get the same answer as the donut on the left from the donut on the right, because in your computation, C5 and C6 would be computed, you would compute positively along C5 and C6 when you did the top half, but then you would get the same result negatively for C5 and C6 when you did the bottom half. And so when you divide these regions into pieces, the extra divisions always cancel out, and that's why you can divide problems into pieces versus doing it all at once and still get the same answer. So if you're like me, you're thinking, what the heck? A line integral that computes the work along a curve is going to be equivalent to a double integral evaluated across the region the curve bounds? How can that possibly be true? Well, the mathematical explanation is a little bit long. So instead of putting it in this video, which is already pretty long, I made a second video. It's called 14.4 Green's Theorem Part 2. So if you're so inclined, if you're a bit worried, if you're concerned, you can stop this video, watch Part 2 now, and then come back to this video. Looking at Green's theorem in reverse leads to an interesting corollary. So let's look at the integral that integrates over the area of the region R. If we call that the difference of those two partial derivatives a function, which it will be, it'll be a function in x and y, then if that function were to equal 1, we would get the area of the region. So this is going to be another way of figuring out the area of a region. But how do we pick P and Q so that this will happen? Well, for example, if f is just 0I plus xj, then when we apply Green's theorem, we get 1 minus 0. Or if we let f equal negative yi plus 0j, then when we apply Green's theorem, we get 0 minus negative 1 for the partial derivatives. And in both cases, we get a 1 in our integrand. And so this is a way of computing area, which leads to the corollary. Corollary to Green's theorem. The area of the region R bounded by the positively oriented smooth or piecewise smooth simple closed curve C is given by these three different line integrals. So now instead of, if we're interested in area, it's possible to do that with a line integral. The first one we don't really use, the one with the half. That's just part of the corollary. What we're going to do is we're going to use one of these two, whichever is going to be easier to integrate. Now, of course, you're going to have to have a way of finding the boundary curve. Now, to evaluate this single integral, we parameterize C and convert x and y expressions into t expressions. And so if you can't parameterize C, then there's no point in doing area this way. You just go back and use your old methods. Divergence of a vector field. Consider a thin layer of liquid spreading over a flat surface. Steady flow means that the velocity of the liquid depends on density and the xy position only, and not on what time it is. So this is a narrow definition here that we're going to be able to work with. So for example, a waterfall, if it's in an ideal situation, that the speed of the water falling would depend on whereabout it is in the waterfall, not on whether it's Tuesday or Wednesday or 5 o'clock or 7 minutes after 5 o'clock. Now the waterfall example is actually three-dimensional, and we're not going to do three-dimensional divergences and so on until a later section, but I couldn't come up with an example in 2 dimensions from real life. Now if f of xy is the velocity vector field of a steady liquid flow, then the value of the divergence at the point xy gives the net rate per unit of volume at which the fluid is flowing away from or diverging from that point. And that's what it measures. And so in particular, divergence, given a vector field representing the steady flow of some medium with density delta, and our vector field delta times the velocity vector equal mi plus nj, then the divergence is given by the following. Now that upside down triangle is pronounced del, so it's del dot f. This is definitional, and that's kind of slang notation because you've got sort of naked partial derivatives dotted with f, mn, and so what you really need is the expression on the right there. Partial derivative of m with respect to x plus the partial derivative of n with respect to y. Flux of a vector field. Flux is the rate at which the fluid is flowing out of a region R across the boundary curve C in units of mass per unit of time. So in order to figure out an integral for this, we take a look at this region R bounded by the red curve, and delta S is the change along the curve, and the green parallelogram represents the liquid flowing out. And we have a unit normal vector n. Notice that that's lowercase n. That indicates that it's a unit vector. And then we have the velocity vector flowing in a different direction. So there's an angle between the perpendicular n and the velocity, the direction of the fluid and its velocity. And then the area of that green parallelogram then will be approximately the flow of the liquid out. And then when we create our integral, delta S will go to instantaneous ds. So here's a blow up of the parallelogram. We want the area of that parallelogram. And so notice that I dropped a perpendicular because we're going to need the height of the parallelogram, and that the base is a straight line rather than a curve, so it's approximately delta S. And when delta S goes to instantaneous ds, that will work out. Notice that at the top of that triangle then we have theta, the same angle as the angle between n and v at the bottom. So we can figure out the height in terms of the velocity vector and the cosine of theta using trig, and then we have a formula for cosine of theta when it's an angle between two vectors, and so we use that, v dot n over the lengths of v and n, and the length of v cancels and the length of n is just 1 because we said that was the unit normal vector. So now the area of the parallelogram is approximately the height, which is n dot v, or v dot n, same thing, times the base, delta S. And if we want to know, if we want to take into consideration the density, then we just multiply the area by the density, and that'll give us the amount of mass leaving. So then for our integral, delta S goes to ds, and delta v is our f function, because we said that on a previous page that we would define f to be the density times the velocity vector, and so we dot that with n and multiply by ds. So there's our integral for computing flux. Continued. If f of xy equals density times the velocity vector for the vector field of a steady liquid flow, Then the flux is given by the line integral, f dot n ds, and gives the rate in units of mass per time in which the fluid is flowing out of the region R enclosed by C across said boundary C. Now, you might have a case where part of the curve the fluid is flowing out of the region, and for part of the curve the fluid is flowing into the region, in which case the flux will equal the mass flowing out minus the mass flowing in per unit of time. So it all depends on the application. So now let's look at the relationship between divergence and flux. Recall that we said earlier that divergence, given a vector field representing the steady flow of some medium with density delta and vector field F equaling delta times the velocity of the fluid flowing equal mi plus nj. The divergence was given by, now that little upside down triangle is pronounced del, so it's del dot f, and it's kind of a slang notation. What you really need then is the result on the right, partial derivative m with respect to x plus partial derivative n with respect to y. And the flux was given a vector field representing the steady flow of some medium with density delta and vector field delta times the velocity vector, mi plus nj. The flux is given by the line integral f dot n, which is equal to the double integral del dot f dA, and so then del dot f is the divergence. And so basically what you're doing to get flux is integrating the divergence over the region. Now, intuitively, why is this true? Well, flux, if you think of the first line integral, flux is the flow of the liquid across the boundary out of the region, how much is passing over that boundary. And the divergence tells you the amount of flow away from each point in the region. So if you think about it, the flow away from each point in the region is going to be equivalent intuitively to the flow across the boundary. And so that's why it works intuitively. Now in the next slides, we'll show why it's true mathematically. So here's our picture again of the region bounded by the red curve C and the normal unit vector n, and then that green rectangle is a tiny bit of the flow, and this is all on the xy plane, so again it's flat. So the curve can be parameterized by r of t in the counterclockwise direction, which means that the derivative vector, r prime of t, is going to point to the left and be tangent to curve C. And so we can form the unit vector t tangent to the curve by dividing r prime by its length, which we'll call v, and then r prime, of course, is dx dt comma dy dt, and if we bring the 1 over v in, then the dt's turn into ds's. Now note that a unit vector crossed with another unit vector perpendicular to it creates a third unit vector perpendicular to both of the original unit vectors. And that's because the two unit vectors form a parallelogram that's a square, a 1 by 1 square, so the area is 1, and therefore the perpendicular vector from the cross product will have length 1. So that means that if I cross r prime with n, what will I get? Well, I'll get k, the unit vector in the direction of z, pointing out of the page towards us. And likewise then, if I cross t with k, I should get n. And so I'll temporarily make t and k into a three-dimensional vector so that I can cross them. And when I cross them, then I'm going to get n. So here's the determinant with t across the second row and k across the bottom row. And we're going to do it the shortcut way by copying the first two columns. And notice that all the diagonals are 0 except that one going down and that one going up. So it's the bottom one minus the top one. And we can change it back to two-dimensional again because it's n on the xy plane. So there's what n actually equals, dy ds comma negative dx ds. So if we go on to the next page, there's n. and f was m comma n, where m and n are the component functions in x and y. And so our flux integral is f dot n ds, and so specifically that's m comma n dot dy ds comma negative dx ds. Carrying that out, we get that integral, and then we can bring the ds in and get a more familiar line integral, and then rearrange it so that your dx comes first. So now here's Green's theorem. And when we apply Green's theorem, notice that the function in front of dy comes first. And so we get the partial derivative of m with respect to x, and then we subtract the partial derivative of negative n with respect to y, and so the negative goes away, and that's why we end up with a plus. And this is what we were going to show. Okay, so now we've covered an awful lot of territory and had an awful lot of integrals and formulas, so let's stop for a minute here and review all our formulas. Work done by force P comma Q to move a particle along curve C. That's the line integral f dot t ds, which can be changed to p dx plus q dy. And if it's convenient, you can just use that line integral to compute work, or you can apply Green's theorem and change it into a double integral using some partial derivatives. So whichever works better for any particular problem. Then we talked about a line integral that computes the area of the region R bounded by C. So we can use a line integral to compute area, and we developed that by going backwards from Green's theorem, back from a double integral to a line integral. And next, we said given a vector field m comma n, then the divergence of f we showed was defined basically to be the partial derivative of m with respect to x plus the partial derivative of n with respect to y, and given that the vector field was density times velocity of a fluid flowing through the vector field, then the flux was given by this line integral, which we have just recently shown is equal to the double integral of the divergence of f with respect to the area of the region. So you may want to stop this video and jot these down. This is all you need to do your problems in this section. For numbers 1 through 12, use Green's theorem to compute the line integral p dx plus q dy. Now notice that the circle, remember what does that mean? That means that C is oriented counterclockwise and that it's closed. It's a closed curve. Number 2, p is x squared plus y squared, q is negative 2xy, and c is the boundary of the triangle bounded by the lines x equals 0, y equals 0, and x plus y equals 1. So here's the region, and if we did the line integral, we'd have to change the boundary, which is a piecewise smooth curve, into 3 separate curves and do 3 integrals. So instead we're going to use Green's theorem and evaluate it using the double integral on the right there. So we have to compute those partial derivatives. Well, if you look at q, the partial derivative with respect to x is just the coefficient negative 2y, and if you look at p, then the partial derivative with respect to y is 2y because the x squared goes to 0. So that's going to be nice. Our integrand is just going to be negative 4y. Now, our region is both vertically simple and horizontally simple, so I just arbitrarily picked vertical simple to set up my iterated integral. So I'm going to integrate with respect to y first. So my integrated integral, y is going to go from 0 up to the curve C1, which is, if you go back up to x plus y equals 1 and solve for y, you get 1 minus x. So y is going to go from 0 to 1 minus x, and then x is going to go from 0 to 1. And so now we're going to integrate with respect to y first, and that's pretty easy. Negative 2y squared, evaluated from 0 to 1 minus x. And then substituting 1 minus x for y, we get negative 2 times the quantity 1 minus x squared. and you could multiply that out, or just go ahead and do a backwards baby of -1, and then you need a 1/3 to take care of the 3. And that's going to be evaluated from 0 to 1, which gives us 2/3 times 0 cubed minus 2/3 times 1 cubed, which equals -2/3. Number 4, this time p is x squared minus y squared, q is xy, and c is the boundary of the region bounded by y equal x and y equal x squared. So it's going to be similar to the previous one, except this time our boundary is made up of 2 smooth curves. And so we're going to apply Green's theorem and do a double integral with respect to area rather than the line integral. So if you look at q, again, the partial derivative with respect to x is just y, the coefficient of x. And if you look at p, the partial derivative of p with respect to y is -2y. The x squared goes to 0. And again, you have a choice with your area because it's vertically and horizontally simple. But it's going to be easier to do vertically first because we have y in terms of x. And so in our iterated integral, y can go from the bottom curve x squared up to the top curve x without having to do any solving. And then x then goes from 0 to 1. And y minus -2y is 3y. So again, our antiderivative is simple. It's 3/2 y squared, and we're going to evaluate that from x squared to x, which gives us 3/2 x squared minus x to the 4th. And then we're going to integrate that with respect to x, so we get 3/2 1/3 x cubed minus 1/5 x to the 5th, evaluated from 0 to 1, which gives us 3/2 times 1/3 minus 1/5 minus 0. When you plug the 0 in, you just get 0. And that simplifies to 1/5, so that's a nice answer. Number 8. P is e to the x sine y, and q is e to the x cosine y, and c is the right-hand loop of r squared equals 4 cosine theta. So here's a picture of r squared equals 4 cosine theta, and the right-hand loop is shaded in purple. So again, here's Green's theorem, and our partial derivatives. Looking at q with respect to x, we get e to the x goes to e to the x, and cosine y is just a coefficient. And then looking at p, taking the partial with respect to y this time, e to the x is a coefficient, and the derivative of sine y is cosine y. Well, what the heck? That's going to equal 0. And so if we integrate 0, we're going to get 0. Now, how can this be? How can the value be 0? Well, if you take a look at the graph, theta is going to go from 0 to pi to get that purple loop. And so if we go from 0 up to the top of the area, p dx is negative and q dy is positive if you check values, because for example, the cosine value is going to be positive there, and the sine value is going to be positive, but we're going backwards along the x-axis, so dx is negative, and dy we're going up, so dy is positive. Now as we go down the other side of that top loop, then dy now becomes negative, and we're from 0 to pi over 2, so cosine and sine are both still positive, and therefore p dx is negative and q dy is negative at this point. And then when we come down the underside, now we're past pi over 2, and so cosine is going to be negative, but sine is going to be positive. And dx, we're going to the right, so dx will be positive, and dy we're going down, so dy is still going to be negative. And so if you look at that, then now p dx is positive and q dy is positive. And as we come up the other side, again, cosine is going to be negative, sine is still going to be positive, and this time we're moving to the right and up, so both dx and dy are positive, and so we get p dx positive and q dy negative. And because of the symmetry, then all of these cancel out, and you do get 0. number 12.5. Now, the reason this is 12.5 is number 12 came out 0 again. So I didn't want another example where the integrand came out 0. So I took number 12 and changed it a little bit. So p is going to be negative y cubed, and q is going to be x cubed. And the curve is going to be r equal 1 plus cosine theta. So here's what it looks like. And to get the whole curve, we go from 0 to 2 pi. So here's Green's theorem again. And if you look at q and take the derivative with respect to x, you get 3x squared. And if you look at p and take the derivative with respect to y, you get negative 3y squared. Now, simplifying that a little bit, we get 3 times the quantity x squared plus y squared. Yay, because x squared plus y squared is what? R squared, right? So now we can change to polar form, so it'll be a lot easier. And so we start off with 3r squared over the area. R goes from 0 to 1 plus cosine theta, and to get the entire region, you need theta to go from 0 to 2 pi. And then don't forget that dA becomes r dr d theta. There's an extra r that's not obvious intuitively, so don't forget that. So then that simplifies to 3r cubed dr d theta. Now it's antiderivative time, and we get 3/4 r to the 4th evaluated from 0 to 1 plus cosine theta. So now we've got the integral from 0 to 2 pi of 3/4 the quantity 1 plus cosine theta to the 4th. Now you could multiply that out, use a bunch of identities, integrate it by hand, blah, 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 but that would take quite a bit. So instead, I just use the calculator at this point. Once you get down to a single integral, feel free to use your calculator. And we get 9 pi over 4. Now the reason I got an exact answer there is I took my calculator answer and divided by pi and got 9/4, and that's why I knew it was an exact value. Number 16. Use Green's corollary to find the area of the region R between the graphs of y equal x squared and x equal y cubed. So there's the picture. Notice that x squared is on top and y cubed is on the bottom. And here's Green's corollary. So we can find the area using any of these 3 line integrals, but we have 2 curves. And I just chose arbitrarily to use the last one since it doesn't have a negative sign. So that's what I decided. But there are 2 curves, the top and the bottom, so I have 2 line integrals, x dy. And now I need a parametrization that goes counterclockwise. So for y equal x cubed, I just let x equal t and y equal t cubed. There might be another way to do this, but that was fairly easy. And therefore, if t goes from 0 to 1, we're going to go from the bottom of the curve, the bottom curve, up to the top. And so we're going to be moving counterclockwise. And now I need to come down the x squared in order to continue counterclockwise. So this time I let x equal t and y equal t squared, but I let t go from 1 to 0. That way, we're starting at the top at 1, 1 and going down to 0, 0. So now my integrals in terms of t, x for the first one, x is t, and then the derivative of y is 3t squared dt, going from 0 to 1. That's the parameterization of x cubed. And then for the second one, I'm using the x squared, and so x is still t, but now dy is 2t dt, and t is going from 1 to 0. So now I just simplified that and integrated and evaluated, and doing a little bit of arithmetic, we end up with 1/12. So the area of that little green region is 1/12 unit, 1/12 square unit. Teeny tiny. Number 18. Use Green's theorem to calculate the work done by a vector field along the circle x squared plus y squared equals 9. Okay, so here's the circle, and the formula we want to use for work done is as it has been. The only difference here is if we're going to apply Green's theorem, we have to assume that the curve is counterclockwise when you parameterize it. So using Green's theorem, we're going to integrate over the area using this formula. And so we set it up, arbitrarily choose to integrate with respect to y first, since the region is vertically and horizontally simple. And so y is going to go from the bottom of the circle to the top of the circle, and then x is going to go from -3 to 3. And if you look at q, that's 2xy, then the partial derivative with respect to x is 2y. And if you look at p, which is y squared minus x squared, then the partial derivative with respect to y is 2y. So you get 2y minus 2y. So what the heck? That's 0. This is unfortunate. Evidently the work going one way is a positive and going the other way is negative, and so it all ends up being 0. Now notice that the odd numbered problems in your book don't come out to 0, so it's a little bit annoying that so many of the even ones did. But once you get the integral set up, which is what this lesson's mostly about, you should be able to evaluate it because you've been doing that for several sections. Number 22, use Green's theorem to calculate the outward flux given by this integral, given that the vector field in question is x cubed I plus y cubed j, and we're going across the positively oriented closed curve defined by the same circle as in the previous example. So here's the circle, and here's the formula. The last integral there was developed using Green's formula, but it looks a little different after they do all the machinations. So we're going to use that last integral, m being x cubed and n being y cubed. So here's a drawing of the vector field, not to scale, and I just drew a few of them. Notice that if we're at 3, 0, for example, then we get f equaling 27I plus 0j. So I didn't make that 27 units long, obviously. And then in the middle of the first quadrant, you get, well, then you're going to get a shorter vector. They're going to vary in size, but I didn't draw that accurately. Now, in the other quadrants, all the vectors are pointing outward, which is nice. So by symmetry, what I'm going to do is I'm just going to use the first quadrant and then multiply that result by 4. And so and again, it's vertically and horizontally simple, so I just arbitrarily decided to integrate with respect to y first. That's actually easier. Well, it's actually the same either way. But anyway, that means that y is going to go from 0 up to the top of the circle in the first quadrant, and then x is going to go from 0 to 3 in the first quadrant. And then I'm going to take that then and multiply by 4 to get the total flux. Okay, so now we look at m, which is x cubed, and the partial derivative with respect to x is 3x squared. And then we're going to look at n, which is y cubed, and the partial derivative with respect to y is 3y squared. So there's our integrand. Integrating with respect to y, we get 3x squared y plus y cubed, evaluated from 0 to the square root of 9 minus x squared. And substituting, we get this messy integrand, which you could simplify and then integrate with respect, you could integrate using trig sub. That would be horrible. So instead I wimped out and used the calculator and got an answer of approximately 381.704. Oops, you know what I forgot that would have made life a lot easier right from the get-go. What should I have done? There's the integral. Yep, I should have changed to polar form. So we're not doing 4 times the first quadrant anymore. We're going to do the whole circle. And so theta is going to go from 0 to 2 pi. R is going to go from 0 to 3. And we're not going to multiply by 4 because this is the whole kit and caboodle. And the integrand, 3x squared plus 3y squared, becomes 3r squared. And then dy dx becomes r dr d theta. So then we take the antiderivative with respect to r, and we get 3/4 r to the 4th, evaluate at 3 and 0, and then continuing, we get 243/4 theta from 0 to 2 pi, and so that comes out to the same answer. But this time we can get an exact answer very easily. So what's the moral of the story? The penguin says, never forget the power of polar form. Oh, do you remember when math was easy? Have fun with these problems in section 14.4.